Okay, so we're starting a new unit on sequences and serieses. The basic construct in this is what is called a sequence. A sequence is essentially just an ordered list of real numbers. So an ordered list of real numbers is basically what we got here. Let's do a couple quick examples. So I can describe a sequence as a sub n is equal to 3n plus 1. So we start counting with 1 as the n. So this sequence would be 3 times 1 is 3 plus 1 is 4. 3 times 2 is 6 plus 1 is 7. 3 times 3 is 9 plus 1 is 10, and so forth and so on. So this is an explicit description of this sequence. So let's try going the other way. Let's say I have the sequence 3/5, negative 4 over 25, 5 over 125, negative 6 over 625, 7 over 3,125, so forth and so on. Okay, so the idea here is I want to be able to write a sub n. The numerator is starting at 3, going up 4, 5, 6. So basically we're taking n plus 2, right? But let's give a little space here because we got to deal with that negative sign. So let's say it's n plus 2 for the numerator. The denominator just powers of 5, so that's 5 to the nth power. And then in front of this, we're going to put negative 1. And let's see, we want n plus 1. So negative 1 squared is positive 1, so that's going to be positive. Negative 1 cubed is negative 1, so that's going to be negative, then positive, then negative. So this is going to create an alternating situation there. So this is a good explicit description for this sequence. All right, so let's get into how do sequences have limits. Okay, so limits of sequences are actually more rudimentary than the limits of functions. Because the limits of sequences only exist when n goes to infinity. So a limit of sequence is defined is that if for every epsilon greater than 0, there exists some k, which is a counting number, such that if n is greater than or equal to k, then the distance between my limit and a sub n has to be less than epsilon. If this is the case, we say that the limit as n approaches infinity of a sub n is L. Okay, so essentially, basically what we're saying here is like as this is like my x-axis and I'm counting up 1, 2, 3, 4, 5, 6, and my values at 1 is this is like a sub 1, a sub 2, a sub 3, a sub 4, a sub 5, a sub 6, and I say, okay, this is L. L is here. I take L plus epsilon up here. I take L minus epsilon. Minus, oops, that's ugly. L minus epsilon down here, so basically building my tube again, right? So there's the L plus epsilon, there's the L minus epsilon, and I pick some value k. Let's say I make k equal to 5, right? So, and let's say this sequence just keeps going along like this. If for every a sub n, where n is greater than or equal to 5, a sub n is within epsilon units of L, then we say that this sequence approaches that limit. Okay, so it's very similar to the idea of a limit as x goes to infinity of a function. We're going to see that these are actually analogous ideas, but this is discrete because these are a finite list of numbers instead of a function, continuous function of numbers. So this falls squarely within the realm of discrete mathematics. Some notable things occur here. We're going to see what other kind of stuff we can pull out of this. So just as like with functions, we also get a squeeze theorem. So this is a squeeze theorem for sequences. Okay, so basically we're saying that if there exists k, which is a natural number, such that a sub n is less than or equal to b sub n is less than or equal to c sub n for all n greater than or equal to k, right? And the limit as n approaches infinity of a sub n is equal to the limit as n approaches infinity of c sub n, and this is equal to that limit L, then lo and behold, if this is going to L and this is going to L, the thing that's in between them, the limit as n approaches infinity of b sub n, also has to go to L. This is not surprising. The theorem works very much the same as a theorem in with the theorem that works with functions. So it's going to move on from there. Okay, so this is a pretty useful one. We're not going to give it a title, but it's a useful fact. If the limit as n approaches infinity of the absolute value of a sub n goes to 0, so it specifically has to go to 0, this implies that the limit as n approaches infinity of a sub n also is 0. So sometimes it's easier to prove that that's going to 0 than it is to prove this is going to 0. But if the absolute value of the a sub n's is heading towards 0, so too is the sequence itself. So we'll take a look at that a little bit later on, but that's a pretty straightforward statement. All right, so we get this idea of convergence and divergence. So let's get those terms on the board. So we want to be able to define the idea of converges versus diverges. So convergent versus divergent sequences. So essentially that if the limit as n approaches infinity of a sub n exists, then we say that a sub n, this sequence a sub n, converges or is convergent. Otherwise, so this is like a switch, it's either convergent or it's divergent. Otherwise, we say the sequence diverges. Okay, so that's two terms. If the limit exists, then the sequence converges. If the limit does not exist, then we say that it diverges. Okay, so some more facts that are relative and similar to functions. We have another theorem that states that if the limit as n approaches infinity of a sub n is equal to L, so that's saying that we're convergent, and f is a function that is continuous at L, then the limit as n approaches infinity of f of a n is the same as f of the limit as n approaches infinity of a n. So this is very similar to when you were working with functions. If f is continuous at the limit, right, then the f and the limit can be swapped, right? So that's pretty simple and straightforward. Normally we are not going to use the definition of convergence to calculate these limits. We'll take a look at how these things are actually calculated here. Okay, so if I want to do, so this is actually a theorem, and this involves the calculation of limits of sequences. This is pretty straightforward. Basically, if an is equal to f at n for all n numeric, right? So all of the counting numbers, and an converges, so that means the limit exists, and f is continuous. Okay, so I have continuous and I have convergence. I have a continuous function and a convergence sequence. Then the limit as n approaches infinity of an is equal to the limit as n approaches infinity, as x approaches infinity, because this is now a function, as x approaches infinity of f of x. So we're saying that if I rewrite the sequence as a function, then the limit of the sequence is equal to the limit of the function. So because of that, everything that we currently know about limits as we go to infinity still works. So let's look at some examples of this. Okay, so one, or a, if I take the limit as n approaches infinity of n over n plus 1, then the two fastest terms are n divided by n is just 1. So that still works. If I take the limit as n approaches infinity of n over square root of 10 plus n, then let's see, this is the fastest term in the numerator is n. The square root of n is the fastest term in the denominator. N goes to infinity faster than the square root of n, so this is going to be infinite. So we say that this diverges. There is no specific limit. C, the limit as n approaches infinity of the natural log of n over n. Okay, so natural log is going slower than a linear, so this is slow over fast, which means we're going to 0. D, if I have the limit as n approaches infinity of -1 to the n, see this is the function -1, or this sequence -1, 1, -1, 1. This thing just oscillates. So something that's oscillating back and forth is also called divergent. Okay, so oscillating is still a form of divergence. However, not everything that alternates is going to be divergent. So let's take the limit as n approaches infinity of -1 to the n over n, right? Well, this, according to the earlier theorem, is going to be the same as the absolute value of it, so long as that absolute value happens to go to 0, and the limit as n approaches infinity of 1 over n, which is 0. So this whole thing ends up being 0. Finally, like if I have the limit as n approaches infinity of the sine of pi over n, this, we can swap this because the sine is continuous. So this is going to be the sine of the limit as n approaches infinity of pi over n, but pi over n as n is going to infinity is going to 0. So this is going to be the sign of 0, which ultimately is 0. Okay, so there's some examples to look at as far as limits, their convergence, and their limits, sequences, their convergence, and their limits. There are some special cases we want to be aware of. Okay, so let's talk special cases for limits. First one is what we call the harmonic sequence. Harmonic sequence is just a(n) is equal to 1 over n. This one does converge. So if I take the limit as n approaches infinity of 1 over n, I get 0, so the harmonic sequence does in fact converge. We have a thing called the alternating harmonic sequence. So in this case, we're going to take the limit as n approaches infinity of negative 1 to the n over n. So this thing is like the harmonic series. Sorry, don't need the absolute value bars there. As n approaches infinity of negative 1 to the n over n. Okay, so like the harmonic sequence, the alternate harmonic sequence we saw earlier, if I take that absolute value, is in fact going to go to the same place that the harmonic sequence goes, which is 1 over n, which goes to 0. So both of these converge as sequences. Now, we're going to see later on when we do a harmonic series, the harmonic series does not converge, but the harmonic sequence does, the alternating harmonic series does. But here, both sequences, just the lists of numbers, actually converge. Okay, we have a geometric sequence. Geometric sequence is something where a to the n is r to the n. Okay, so if the absolute value of r is less than 1, then the limit as n approaches infinity of r to the n is going to 0. If the absolute value of r is equal to 1, then the limit as n approaches infinity of r to the n is just going to be 1, because it's going to be a list of 1s. And otherwise, i.e. r is, so the absolute value of r is greater than 1, we say r to the n diverges. So it will only converge if I am less than or equal to 1. The geometric series, if r is greater than 1, diverges. So these are 3 special cases to be aware of: the harmonic sequence, the alternating harmonic sequence, and the geometric sequence. All right, so that's the beginning of sequences. Next time around, we'll start building series, and there we go.